Series and parallel circuits. Circuits can be simple or they can be very complex. So we'll take a look at some simple ones first. Here is a very simple series circuit. Here's my power source. Instead of a battery, I have a whole power plant. Here's my conductors that are flowing into my electrical load. This could be a residence, it could be a city. Whatever it is, this is my electrical load. I'm converting electrical energy into all different kinds of other forms. And then I don't use it up. I don't use up those electrons. They're just flowing through. So that when you say you're using electricity, you're not expending it. You're kind of borrowing it because you're spitting it right back out again. It's that motion, that flow, that's just like water turning a water wheel that gets the work done in your devices. This is like the water company spitting you out the water. You've got all your little water wheels that are lighting lights or whatever they're doing. That water keeps on flowing. They're just charging you for the supply. These are some simple devices that you would see in most circuit protected devices. We said last week, they're not there to protect you, they're there to protect wires. They're essentially fire protection devices. If you try to put too much current through a wire than what it was designed for, the friction that's created is so great that the heat be generated enough to melt off insulation, and that might cause a short circuit that even has more current flowing, and it can start fires. And then conductors, we've talked a little bit about circuit board traces, cables, wires, anything that's carrying the current to the load is a conductor. Control devices, because I don't always want current flowing to my loads. I don't want the lights on when I'm trying to sleep. I can interrupt the flow of current with these control devices. Like switches, where I manually do it. Thermostats, an example of an automatic switch. And dimmers, an example of a variable control. Load devices are anything that takes the electrical energy and converts it into some other form. In this case, we're converting to light or motion, mechanical energy. Some common schematic symbols. It doesn't take too much imagination to see how these came up. This is a switch that you're going to just throw into place. This is the push button switch. This is a breadboard. We'll talk more about breadboards later, and you'll be using them in the lab. But the way this works, here's my voltage supply, 9-volt battery, and I'm hooking up positive to this hole. All these holes along this way are common. When I say they're common, I mean they're all touching one another. Whenever you talk about a circuit common, that means where components come together to a single point. Underneath of this is a strip of metal so that if I put something into this hole, there's continuity between that hole and the next one. Any hole along this line is the same electrical point. And the same thing down here. I come in here with the negative, put it into this row. Everything along this row is common. So this point, this hole is the same as this hole electrically as this hole is this hole. So now I've plugged these resistors, one at the top here at positive and one down here in the negative. And I've taken another one, done the same thing. This is what it looks like in real world. This is what it looks like represented with the schematic. Everything on this side is common. You can visualize, and you should visualize, as being a single point. This is just the same as if I were touching directly right there. And this is the same electrically if I were touching right there. Now they're looking at different ways to represent. We looked at some schematics. This is a wiring diagram. In wiring diagrams, you actually see the wires and where they're the junction boxes, the devices, and even sometimes like screw numbers and terminal numbers, where things go, where they really physically land. A block diagram just gives you a general thing. Here I've got a speed sensor. This must be on a car, not necessarily, but I've got a speed sensor. I would call this a tachometer because it's looking at rotational speed. Then that gets input into an interface that converts it into a microprocessor. We'll learn a lot more about this stuff too later on. And then it goes back out into the real world. So here's the real world. It gets into the computer here and comes back out in the real world as a digital display. Simple series circuit. That's what it looks like in the real world. That's what it looks like on paper. Get used to seeing what it looks like on paper, because when you go to control rooms or the back of devices or in the box where the breakers are, wherever the instructions are, the owner's manual, you're going to more likely see the circuit represented like this. You need to go, well, in the real world, I'm going to be looking for something that looks kind of like this. So here's something we need to probably take a look at. I've got 12 volts and I have an open switch. And if I looked at voltage across each of these lamps, I've got nothing. There's no current flowing through here. I will see the entire voltage across the open switch. Remember that voltage is the difference between 2 points. And the difference of force, the difference of charge, however you want to look at that, it's a difference between 2 points. You can't get a voltage by just looking at one point. You always have to get a voltage by comparing that point to another point. So in this case, if I were to compare the terminal, negative terminal, to the positive terminal, I would see 12 volts. And if I compared this side of the bulb to this side of the bulb, I've got nothing on either side, so there's no difference between the sides. So there's 0 volts. You know, I'm measuring a difference, right? 12 volts is a difference. So I've got push, I got all this push trying to move something, but I can't. So all this pressure's built up here, maximum 12 volt. On this side, I've got nothing. So the difference between this full force and nothing is 12 volts. Down here, however, I've got current flowing, and across the switch, I've got 0 volts. Why? Because a closed switch puts each side of it common, so there's essentially a short circuit or the same point. There's no difference between these 2 points, and voltage is the measurement of the difference between points. The difference is nothing. That's like if you're standing on a square and you want to measure how far it is from that square to the same square. It's nothing. There's no difference. But from here to here, across these lamps are 12 volts. But notice this, and we'll talk more about this in subsequent lessons. Notice that these lamps, because they're equal in resistance, the voltage is equally divided among them with 4 volts apiece. That's an important characteristic of how series circuits work. That's something you should know. Again, we'll kind of look at it more in depth later, but this is a good way to catch wind of it now. Here are 2 series controls. To make this light come on, what do I need to do? Close one, doesn't do any good. This can be a logic circuit if you wanted to think of it that way, because logic is supposed to solve problems. Let's say I'm a design engineer at a place, and the production foreman comes to me, and he works at Fenton Glass, and he says, you know, I got a problem here. I've got a packer at the end of the conveyor. He's packing glass that comes off the line, and I have a couple of guys inspecting it. And they sit there, there's a light on the other side of the conveyor, so this glass work comes between them and the glass, and they can look through the glass and see if there's any bubbles or cracks, any kind of flaw. And if there is, they don't want a Fenton label going off, so his job is to pull it off and smash it so that it can never be packed away as Fenton. Just to make sure they have another person on down the line that does the same thing. That way, by the time it gets to the packer at the end of the conveyor, you've got 2 things in place to make sure that's going to work. So as a production foreman, it's like, I've got a problem. Sometimes these guys are getting up and going out to smoke, and there's just one guy there. Sometimes there's neither guy is there. I need to find a way to keep that from happening. It's like, I can take care of that. So what I do over here, instead of having this as a light bulb, I say this is your motor that goes to your conveyor belt. And these little switches, these are going to be under the seats, just like on your riding lawnmower, your seat belt switch under your seats. And by gosh, one of them sits down, won't work. Both of them's got to sit down before that conveyor can run. They've got to both be in their seats for that conveyor to run. If either one of them gets up, it's going to stop. Here we have loads in parallel. Notice that in parallel, this point, and this point are all common, all the same point, all the way along here. It doesn't matter how long this line gets, in theory, it's all the same point. And on this side, because this is a closed circuit, these are all the same point. So this point, this point, this point is the same as this point, same as this point. So there's 12 volts across all of them. In this case, in a series circuit, we saw that the voltage was divided proportionally among the loads. Here we see that they all have the same voltage, but what's different is the current. This is what you maybe saw before. This is showing the connectors where you plug in your leads. Then it shows different settings, different ranges. This continuity checker makes a beep. You put it on a piece of wire, and if it doesn't have a break in it, it'll beep. It'll also read 0 ohms. Okay. All right, measuring voltage. You measure voltage in parallel. You got the red lead to the positive, you got the black lead to the negative. It's reading 12.6 volts. I'll say this, most power sources, batteries, and even out of power supplies will read higher under no load conditions. And then when you put something on them, load, the voltage will drop some to where they're supposed to be. It's normal, it's expected, and they calculate all that out. From here, I'm saying this side, this is positive with respect to this side. But if I switch it, the opposite is true. This side is negative now compared to the other side. Amp meters, you have to hook in series. If you hook an amp meter, take the probes of an amp meter and you hook it up like this, you can damage it. So you have to open the circuit up so that the current will leave the source and go in the amp meter on one lead and then out the other side and then go into your load. If you don't do this, you can blow up your amp meter. A clamp-on amp meter gets away from that, but there's some limitations. We're going to learn that whenever electricity runs through a conductor, it creates a magnetic field around it. This device will read that magnetic field and can tell how much current's flowing through there to create that amount of field. So this is a clamp on. The thing about this is it has to be only across one wire. So if I've got an appliance like on a lamp, this is a lamp cord, there's 2 wires in there, one going to the lamp and one coming back. And if I put an amp meter around that, or an air conditioner that's plugged in the wall, it's going to say 0 because the magnetic field that's being caused going into the load counters the opposite magnetic field that's created as it's coming back the other way. So both of those two things negate one another and it'll say 0. Measuring resistance, turn off the power or you'll blow up your meter, or even at best you'll get wrong results. And you also have to remove one side from the circuit, because if I wanted to measure this resistor and I put one lead here and this was still down here, I would be reading everything else in the circuit. I've got to isolate one end so that the meter can read into this and not have a complete loop. So disconnect one end of the resistor, disconnect the power. Single wire automotive circuit. Okay, I got my battery for my car, an insulated wire. Here's my light. Here's my switch. This switch is normally closed. So when I close the door, that opens the switch and the light goes out. And now when I open the door, the switch will close, the light will come on. Once that door is in a position where this switch closes, the current leaves, goes through the load, it gets to here and it's marked as going to ground. You notice that this is also at ground. So it's grounded to the frame of the car. And that allows the frame of the car to be a conductor. So the current flows through the load, through the closed switch, into the chassis, along the chassis back into the battery. So there's my continuity. It doesn't stop here. It's actually common or connected to here. Solid wire and stranded wire. Imagine your extension cords if they were stiff wire and you had to roll them up every time and unroll them. They're just not made for that, and they will break over time. So solid wire, a good application for that is where you're going to put wire up and you want it to stay there, like when you're wiring your house and you bend it and it kind of just stays there on its own. You might have to put a staple here and there. But stranded wire is really good and flexible. It's a matter of flexibility. Printed circuit boards, you've seen the traces on a board, they're conductors. American Wire Gauge came out that standardizes wire. The thing to note here, as you can see, as your numbers get smaller, the wire gets bigger. Some applications, lighting, receptacles, typically 14 gauge, 15 amp circuit breaker. 15 amps going through a 14 is safe, and that's what it's designed for. I've got 12 gauge because it's carrying 20 amps to make that particular device do its job. Heavier current requires heavier conductors and circuit breakers. If the power company charges me 13 cents per kilowatt hour, how much will it cost me to run the circuit below for 24 hours? And apparently this was on a test at some time and could show up again on a test. So might want to take a look at this. Well, I want to know how much it's going to cost me. I need to first know, if they're charging me 13 cents per kilowatt hour, how many kilowatt hours do I have? What is a kilowatt hour? A kilowatt hour is kilowatts, or 1,000 watts, times hours. Okay, well, I've got my hours. There's 24. So I've got that part of kilowatt hours, 24. Now I have to come up with the kilowatts. So how do I figure out what kilowatts? Well, watts is power. So to get power, I use that little one of those formulas. But I'm going to use probably, for me, because I could use voltage times current, but I don't have current right here. So I'm going to use what I have. I've got volts and I've got ohms. And one of those formulas for power was volts squared divided by ohms. So I'm going to take 120 volts times 120 volts, and that is 14,400, and divide that by 12, and that gives me 1,200. 1,200 watts, but there wasn't kilowatts. So to get kilowatts, which are 1,000 watts, I have to take my watts and divide it by 1,000, and then I get 1.2 kilowatts. Now that I have kilowatts and I can multiply it by 24 to get kilowatt hours, each one's 13 cents. I come up with, it's going to cost me $3.74. So that's how you solve a problem like that. And in doing that, somebody says, well, look, I'm thinking about getting this water heater or this, whatever this device is, a motor, a fan for whatever it is. And you need to kind of give them an idea what it's going to cost. This is what you do. It's like, how long is that thing going to be on every day or a month? And with those kind of numbers, you check with the power company, see what their rate is. You can give them the cost of using that device for the need that they have over a period of time.